Thank you.
Yeah, welcome. As you can see, even the pronunciation of iOS XE is not easy, so we'll try to show you that it is not that easy, not that complicated. So my name is Piotr Kapiusiewicz. I'm VPN Lead in Krakow TAC. TAC meaning Technical Assistance Center. So we are the technical geeks and working in technical stuff. This is Oliver, my friend.
Yeah, so I'm Olivier Pelerin. I'm working out of the TAC in Brussels in the escalation team, mostly dealing with architecture and VPNs.
Okay, so the first question, how many of you have seen or touched or configured ASR 1000? Okay, forest of hands. Yep. So we will split, we will split this session into the three subcategories. First one will be the system architecture, and I will show you how the day in life of normal packet going through or to the box looks like. Then we will talk about the debugging strategies. So how can you troubleshoot how can you troubleshoot the box or the traffic that is going through that box? And we will show it. We will show few, or actually two debugging strategies, and Packet Tracer will be one of them. Okay. And at the end we will show live demo. Live meaning really live. We have the router here on that laptop, so we hope to show you the tool lively.
Yeah.
It might of course break because it's live presentation, right? Live demo. So let's get started with the system architecture. So basically iOS XE, from the iOS XE, it is the operating system and it resides on ASR 1000 series and on ISR 4400. From the end user perspective, it will be the same iOS as you know from regular ISR G1 or G2. So the CLI, the commands, it will be exactly the same. So the telnet SSH and the implementation of control plane protocols like EIGRP, BGP, it will be exactly the same as you know it from the ISR G1 or G2, okay? But it looks the same, but it's not the same. So the iOS XE or ASR 1000 will be here the example. It contains of three main modules. Just by the way, I will reach the hardcore level, let's say it like really technical, and then we will go to the easier part, okay? So don't be scared. Thank you. So yeah, the iOS XE or ASR is built out of three main modules. RP, this is the blue one, ESP, and SIP. I will talk about these modules in a moment in details. But what is the most important here is that RP is the route processor. This is the iOS part. ESP, and I will tell in a moment what it means that this is iOS part. ESP, this is the forwarding module. So the module that is responsible for forwarding packets itself, okay? And SIP, these are the physical modules that you put into the box. So all of them are physical modules. In bigger ASRs, you can just remove them and attach different modules instead. You can see that RP and ESP might be duplicated. It is just for high availability purposes, right? But there is no active mode on ASR. So all of these modules are connected with the forwarding bus. I will talk about it in a moment. But what is the most important part for you to understand, and I hope this is something that you will take from this session, is that on ASR, the packets are actually not going through the iOS itself. So if you do debug IP packet on iOS, you will see nothing, because the packets are going through the actual hardware. So yeah, as I mentioned initially, iOS XE is like iOS, but it's iOS, and you cut off the forwarding plane, you cut off Ceph, Cisco Express Forwarding, and instead you put a piece of hardware. So this is the iOS XE or the ASR. So I was talking about three modules: RP, ESP, and SIP. Let's look in details. What do we have inside? So the RP, the most important process that is running on the top of the Linux there is iOS. So it is the iOS that you know, and this is basically for the console access and for the control plane, like EIGRP, BGP, etc. And the iOS itself is architecture independent. What it means that it does not know what will forward the packets or how the packets will be forwarded. iOS is just communicating with the process which is called forwarding manager on RP. This is different process running on the same module. And this process will talk to the forwarding manager, which is residing or which is running on the ESP. This is this second module, the forwarding forwarding of the packets module, right? So basically, iOS talks to forwarding manager on RP, then forwarding manager talks to forwarding manager on ESP, and forwarding manager on ESP is programming the hardware, QFP, quantum flow processor, and this is this box here. This is the place where all the packets will be forwarded. So all this iOS and forwarding manager part is just to program the hardware, so just to program the QFP. So the last but not least module is SIP. This is like a carrier card to which you just insert the physical ports, so like the gigabit interfaces, etc., right? So we will have here like 3 modules. First with the ports, second one which forwards the data and packets, and the third one which is just the control plane RP, route processor, which is responsible for programming the hardware. It looks scary, and here we are reaching the top of the most complicated part. I hope it will become easier now, since now. So how the packet is flowing through the box. So the packet first enters the physical interface. Physical interface is inside SPA module. Then the packet goes into ingress classifier, and this is really worth underlining here. The packet is classified into 2 queues: low priority queue and high priority queue. At that moment, we are still in the interface card. At that moment, we are classifying packet into low and high priority queue. Why? For instance, if you have a scenario in which ASR is under heavy load, like there is a DDoS attack or something, we want, for instance, BGP traffic to still go to RP, and we don't want to drop that packets. So we want to treat them as priority. So thanks to that, thanks to the low and high priority queue, we can set up here that BGP is our important traffic, and we want to handle it first. Okay, and this is done in hardware on interface level. So after that, the packet goes into the ingress buffer. From ingress buffer, it goes into ingress scheduler, and from there, it goes into the forwarding bus. Here, this slide is still the interface module, so it is called SIP. So from SIP, after the packet goes through all of these steps, the packet is being forwarded to the most important component of ASR. It is the ESP. And from ESP, it is being forwarded to QFP. And inside or in parallel, we have the dispatcher process. Dispatcher process is the process which, because QFP is actually, these are 40 cores running in parallel. And every core has 4 threads. You will see it in a moment. In reality, ASR can parse 160 packets or more because we can put this in parallels, but basically 160 packets in parallel at the same time. So the role of the dispatcher, this process here, is to choose the free PP and to choose the thread inside the PP, which is free and which can handle the packet. So when we have a PPE which is free and when we have the thread allocated, we are ready to finally parse the traffic and parse the packet. So depending on the type of the packet and of the traffic, let's imagine that we are having IPv4 example. There will be first input features applied. Input features are determined in the array or in the list, which is called feature invocation array. It is the scary name FIA. Or at least this is how we call it in TAC. So feature invocation array, in shortcut, these will be the features which are applied when the packet enters the box. So when the packet enters our ASR, it goes through the SIP physical interface, then it goes here to the QFP, to PPE, and to the thread. And then here we are seeing that the input features are being applied. So it might be NetFlow, it might be input ACL, it might be QoS classification, NAT, etc., right? So after that, there is a switching decision being made. Switching decision, it basically means we want to determine the egress interface. So we know how the packet entered. We know that we need to do some magic with this packet, like NAT, etc., right? And based on the switching decision, the role and the purpose of the switching decision is to determine how the packet will leave the box. So after we know it, after the switching decision is done, by the way, you can see that one of the switching decision is packet for us. And this is the place where the packet will be marked as to go to iOS. So only if packet is determined as packet for us, or in some other rare scenarios, packet can go to iOS. Without that, you will not see the packet in iOS. So if you do debug IP packet, you see nothing. What is worth underlining is that, for instance, ICMP echo reply is also implemented in hardware on ASR. So when you ping the box, when you ping the ASR router, and you do debug IP ICMP, you see nothing. So don't use this as the method of checking if this box is this box. ICMP is not the way to do it. So after the switching decision is being done, we know egress interface, we are applying the output features. So output ACL, NetFlow, again NAT, and other features, right? And other features. So when we are done with this, so the packet went through all the features, input, output features, we are almost ready to send the packet. Almost, because there is QoS. So on ASR, there is a bQoS. It is basically the hardware implementation of hierarchical QoS. So the QoS is also done in hardware on ASR, and whenever the packet is about to be sent, so when there is a proper time for the packet to be sent, the packet is sent back to the forwarding bus, and then from there to the physical, to the module with interfaces being called SIP. In SIP, the packet goes, it comes from the forwarding bus, and it goes out of on the physical interface. Just from our experience, we are both working in TAC. This part here works, so you don't really need to troubleshoot anything here. The only thing you might really do with it is RMA, I mean replace it, right? So this really works. It takes the packet from the port and sends it to QFP, and here you don't really have a problems, at least from our experience. So now how to troubleshoot it, right? I mean, it looks quite scary, and it is quite complicated. So yeah, what are the problems that we are seeing? The packet might be dropped, might be changed to the way that you would not expect it. It might go, to the moon and back, and you might really not know what is happening with the packet and with the packets and the flow. Or actually, the packet might not even reach our box, right? Sometimes we are troubleshooting issues on the router, and these issues are not on this router; they are before, right? So multiple things can happen in real life. There are multiple features which might break the packet or drop it or corrupt it, etc. And aim is to find which feature. And this is usually quite hard. So one of the approaches is to use these commands. I don't want you to know them, and it is just for your reference that if you are really good in architecture, and you are, for instance, this is the scenario of looking for the packet drops. You can go through, you can know architecture by card, and you can know that packet will go this way. And you can check every step here, step by step. This is one approach, so you know all of these commands, and they look really nice, right? If you want to show that you are good, you might use these commands, right? But they are not very. It doesn't really scale, right? So how usually we are seeing customers troubleshooting the issue with the flow not working. We see them first doing show run, and you want to try to understand what is configured on that box. Do we have any access list applied? What is happening on interface? What is the routing, and etc., right? But on the big boxes and with big configuration, it might be mission impossible. Or, for instance, you think that everything should work, but it doesn't. And then what then, right? So then the problems appear. So the troubleshooting of control plane is quite well known. So everyone can do show run and read the configuration. Everyone can do show access list and read the configuration. But what if it is enough, or what if it is not effective enough? Troubleshooting of data plane issue usually is very complicated, or used to be very complicated, and this is something that we wanted to change. And
so yeah, so let's change that. You see that. Basically, from, let's say, classic iOS, we had low-scale box, and troubleshooting was not something that was requiring, a lot of conditions and a lot of ability to just select a flow. So we, in TAC, we have started to initiate with our business unit a simple way for us and for customers to troubleshoot. And this is what we call the packet tracer. And if we go back to the packet processing within the QFP, so if you remember, the packet arrives on the SIP. From the SIP, it sends via the kind of point-to-point link towards the QFP. On the QFP, the dispatcher select whatever core is available and select a thread, right? At this stage, whenever we start to put a condition on this box, So we will put a condition, and whenever it arrives into the packet processing within the thread, we will simply put a packet match. And what it does, it's simply checking, I don't know, I'm maybe looking for 10.1.1.71. And it will check if that packet has that IP address. Or it might check on an interface, that kind of thing. And it will just turn on a debug me flag. And it will just say to the system, please debug me whenever you need. So this is, let's say, the first part of debugging. You will start to match traffic. And so then the packet gets processed. And it goes to the input features, it's going to the routing decision, and then to the output fear. And you see on the right side that we allocate a buffer, and in that buffer we even record every single operation. We can go to that level of saying that packet went into all those operations up to the exit point. And if a feature X decides to drop the packet, it will get reported. So I will know what went wrong. And that's really the most important thing. That tool will allow me to know if I saw the packet, if the packet gets forwarded, or if the packet gets dropped. And it will tell me exactly what to do next, because then you would like to debug a feature. And this has been introduced in 3.10. So as of 3.10, you can follow a flow. And that's something that we will do on a demo. So I have a CSR 1000V, so the virtual version of the ASR 1000, which runs iOS 6e and the same kind of QFPin software. And we will troubleshoot a problem on my laptop. So if we go, Cisco, we like the CLI, so how do we do that? Step one, we put a condition. And you can see here. So we type debug platform condition, and then we put whatever we want. Like, please debug anything ingress, maybe not the best. Debug anything ingress on a specific interface. Or please debug that IP address on the ingress interface, and as well if the traffic will be seen on the egress interface. For instance, if you use IPsec, you might have a crypto map, and the traffic arrives encrypted, and you want to trace the packet as of the time when it gets decrypted, egress on that box. Because you are in the troubleshooting of that feature, you might have started to see if the packet arrived from the IPsec peer, and then you want to know what's happening afterwards. So you have the possibility. It's like a Swiss knife, a Swiss Army knife. All possibilities are available. You can have like this one, like IPv4 access list. So here we just put an IP address without modifying the config. So if you need a maintenance window to add an SCL, here you don't need to do that, because you can do that live. And of course, we get MPLS conditions. So you can search for label in the stack, and you can have IPv6 conditions. So really, a lot of possibilities just to conditionally turn that debug me flag. So step two, we need to enable the packet tracer. So the packet tracer is just a client which is on the QFP infrastructure that will just start to seed all those packets that have the debug me flag turned on. So here is the easiest. You see here we get the condition, and then here we just type debug platform packet trace enable enter. When we do that, we just get very high-level information about what we are tracing. So we don't get to the packet detail, but you just have statistics about what you trace. Like, I have matched 102 packets. Out of those 102 packets, 12 were ingress. And then 90 were inject. Inject means that they are injected from the RP towards the ESP. So coming from iOS, the old iOS, going down to the network. And then you see, like, out of those packets that I've processed, 12 goes forwarded, but I had to drop 90. And those are the reason. So those are the cause of the drops. Like, some got dropped by IPv4 null 0, so well, we had no route. And some were dropped here in this case because on-base firewall was turned on. So I have, for a specific condition, a huge visibility on what is going on in the box. But then you can go beyond that. You can even go at the packet level. So here, again, same CLI, we put a condition, whatever the condition is, And then I say, well, I would like you to trace 16 packets. And we can go up to 8,192. And then I just use the same CLI, I just enable a new command. And now, when I look at show platform packet trace summary, then I have more visibility. I know that we had few packets that arrived from gigabit 002 towards a weird interface, internal 00 RP0. That's basically the view of iOS from the QFP. It knows that that's the RP. And then the most important is the state. Punt. You know, it's a traffic that got punt. And then you have a reason for us control. So that was kind of control plane traffic, which could have been, I don't know, a GRP, BGP, IKE, or whatever you use. And then you have some other packets like those one, which come from inject. Most likely, they came from the RP, and they just reply, and you see that state forward. So there, you see what is happening on a summarized way. But you can go deeper, which is what we do on the next slide. So now I say, well, show me packet 1. And then I have a lot of information, like I know it's an IPv4 packet with that source address, that destination address. Oh, it's an ESP packet. And all the major features that you can configure, such as NAT, zone-based firewall, and crypto, and a few others that I don't remember, but will simply print. We will see like the net flow table and all those things. They will simply print information. And here you see that the info that gets printed says action decrypt. And then, you know, the essay under. So if IPsec doesn't work, you can basically, from the data plane, try to understand what is going on. And here you have the SPI, you have the peer IP address, so you have a lot of information and you have a pure visibility. You can have 4,000 spokes. You will just troubleshoot one. And then sometimes, you know, especially if you think the iOS classic, you see output drops happening somewhere, and you don't know what's happening. And you see drops, but you don't know what's the flow that caused that drop. Well, in the packet tracer, we have added as well the ability to just trace dropped packets. So what we do, so CLI, again, stays very similar. So we put a condition, and then we say, well, I would like to trace the drop packets, and you can put a drop code. I will show you how to do it in the demo. And then you enable the thing, and due to some code constraint, we have to stop the condition prior seeing the packets. That has been a limitation that we have currently. But then you see that here, I know I'm just capturing all the drop packets that use that drop code 53. And I can check all the packets. The rendering of the monitor is not good, but here you would see, the IP address, the peer, and I can even copy the packet. So I get the XDump of that packet. And I can decode it. I can have on the box, it will tell me it's an IPv4, this is UDP, TCP, and I will get high-level information about that packet, IP ID and all those things. So that information will be available on the box. And that has been integrated in 3.11+. So, I mean, this is nice to talk about a feature, but seeing it's sometimes better, because you will see that that thing works. And we will do a small demonstration. So I get here on my laptop a few routers running and one CSR 1000V, which is running XE314, so the version that we will release in November. So let's imagine that as the provider, you might have, I don't know, an ASR 1006 with an ESP200 that will deliver 200 gigs of services to customers. And one of your customers has a problem. And he says, well, you know, I get in a DMZ, which is behind one of your interfaces, I get a database server. And you are providing the service of protecting my device. And everything works fine. I have very complex network, and I have some VPN spokes that are behind the LEAS and PLS network, and I get a lot of customers that are on the internet, and they simply access the database because they need to place orders, so God knows what the customer want to do. And let's imagine that the guy says, everything is fine, but there is just one guy from, I don't know, that place, he can't access it. It doesn't work. Can you help me? And, well, most of the time, it's difficult. Because if you have a device that is feature-rich, that means the config will be kind of lengthy, right? You might have a very good documentation, but it would be 200 pages. Or you might have very bad documentation because it has not been updated. So for people, it's getting very difficult to just enter into that thing. And the only way will be if we use the old way and the old framework, that would simply to go, let's have a look at the config. And that's what we will do.
So yeah, as Olivier mentioned, he will use the CSR 1000V. CSR 1000V is just the like ASR, but all this QFP and things are being software emulated.
Yes. For the people on the back, is it big enough or I need to increase the font size? Small, big? That's good? All right. So we get that box. Normally, let's hope it's still, if things are still working. Yes, it's up, it's good. So, so the first thing that you might do is say, well, let's go to the config. And then you would say, damn, I see a lot of IPsec config, and I see so zone-based firewall config with a lot of zones.
So just to remind what we are doing, we are trying to troubleshoot 10.1.1.71 guy somewhere who cannot access some server.
And you could go into all the configs and you will see, well, I don't know what is the ingress interface. I don't know what features have been implemented on the ingress interface. I don't know if the packet arrived. I don't know if it's the ASR dropping the traffic. So you might simply, and this is typical in TAC, is sometimes you get a P1 and you need to learn the config and we lose 1, 2, 3 hours because you have no other tools to do it. So here we have the chance of saying, well, no, we have a tool to do it, which is a tool that has been engineered to be live, to be supported. If there is a problem, it will be fixed by the development guys. And so let's try to do that. So what did we say? We had the IP address 10.1.1.71, right? So we put a condition. So I don't want to modify the config because I don't have the privilege to do that, for instance, because I need a maintenance window and it's urgent. And I say, well, let's just match that traffic ingress. At this stage, nothing is happening because we all did once in our life when we were young, debug IP packet enter, box dies. I did it. And I don't want people to do that. So to make starting to have that debug flag turn on, we need to start.
Of course, Olivier never did it on TAC case, right?
No, I did it on my system, on a previous live. Then, let's simply start to trace those packets. Well, let's pick up around 128 and just enable them.
Yeah, so as Olivier mentioned, this is like fully supported solution and it is also designed to run on the production, right? So you don't need to go into maintenance window to turn on it, right?
Yes, exactly. So CPU-wise, you might expect between, let's say, 2% and 20%, depending on the packet rate mostly and the level of information you want to get of the tracer. But I have seen, we were testing it on some platforms and we saw no noticeable effect. So it's very light. It has been designed for production. So here, you see, it's working. We could match a packet. And here we have a drop reason, which is IPv4 ACL. So now, logically, you say, well, let's have a look at that packet. So it's packet 0. And here we see, so we see that we get a packet that arrives on gigabit 1. You see output gigabit 1. It doesn't mean that the packet did a U-turn. It just is the latest interface where the packet was present, this last interface, let's say. And you see a drop reason. And you have some information about that packet. So I know the source port. I know the destination port. I know it's a bit drop. So here, Now you can go back to the config because you will say, wait a minute, it arrived on gigabit on interface gigabit 1. All right, I have an ACL on gigabit 1, so that's the feature that dropped the packet.
Yeah, and you can see that on this interface we are having different features like zone-based firewall. So without that tool, you would need to analyze first the zone-based firewall, then the ACL, then there is a NAT. So multiple places where something could go wrong.
You would
right?
have to shoot in the dark, and here you pinpoint the guilty feature directly. So here, for the sake of the demo, I'm not going to troubleshoot the ACL. I don't know exactly what lines is my problem, because we don't have the time for that. No, it's no 90. And here, normally, if we are lucky, so the packet tracer still run, right? And, now we see the effect of the modification of the ACL. So now, from all the drop packets, we see forward. So now, someone says the system doesn't work, I have the visibility that the QFP didn't drop the packet. And knowing that the rest of the architecture is kind of passive, you have a good proof that you need to troubleshoot on the next box. So just for the sake of looking at what's the output when it's working, so let's pick up.
Yeah, sometimes the packet might be forwarded, but not where you would like it to be forwarded. Or it might be knotted in the way you wouldn't like it to be knotted, right? So,
yes, but
so you can check now with even the working scenarios, right?
Yes. So if I would have NAT, I would have seen the post-NAT address getting printed. And so here you see that I have the ingress interface, the egress interface, the state, which is forward, and then the major features that went through the box. Here, IPv4, we have the IP address information, and ZBF, zone-based firewall, the state. More important, because sometimes it shouldn't be forwarded. The system will tell you, well, this is the zone pair, and this is a class map. So you can then go back to the config and say, wait a minute, I have overlapping ACLs. This traffic should have been dropped. And you know exactly in each of the subsystems where exactly it went.
So yeah, it might remind a little bit the packet tracer from ASA if you were using one, right? It is something similar, but here it is implemented in hardware and it is for real traffic, right? So it's not a simulator or anything.
So now if we talk about, do we have 5 minutes we still have? Oh. So we could even drop, just capture drop packets, which I will do very quickly.
So can you maybe show how to gather the drop codes?
Yeah, so I will take the show platform hardware QFP active. I know it's a horrible command, but we are trying to fix it. And
so this is just for information, the command that is showing you everything that QFP dropped. So you can do it multiple times and, for instance, see where the counters are increasing. This is one of the methods that we used to use before the packet tracer, right?
Yes.
So we are just blindly looking at the counters, right?
So there I will just use that drop code 213.
Yeah, now we can see, for instance, what is under code 213, right? And what are these packets which are there, right? Why this counter is increasing.
And what about if we copy the packet? Because I want to see the packet that I drop. So I will say, well, just drop them on the output part because that's where it's where I will see it in that scenario. I won't maybe see it at layer 2 or at layer 3 or at layer 4, depending on what I'm looking for. I will just get the default, and I can define the size. And I need to enable, so 256 again, and enable. So show platform packet trace configuration, that will give you all the things that we did. So you know that you didn't forget, like, I don't know, to trace any packets and things. And now we will wait for the problem to occur, which should be like immediate. So let's see. Okay, here we just captured the IPv6 packets that I was looking for, which is that IPv6 unconfigured FIA, which is a drop reason, and maybe you are interested to know why. So for implementation standpoint, we can't check the packet itself while it's capturing, so I have to stop the condition.
So we cannot see what happened with this packet. We cannot see the steps because the drop is after. And we are learning why it was dropped too late. We are not capturing all the information for all the packets, We are just storing the packet. So here, for the drop reasons, you cannot see what happened with the packet. You can just see the packet itself. So you can see it in the hexadecimal, which is not very readable, and you can also, I mean, for some it might be, but you can also decode it, right? So it is like in a little bit better form.
So if you, like me, breeding hexadecimal overnight, that's enough, but I'm lying, so I like to decode that thing for me. And I have the information, so I know what packet arrived, and then I say, well, wait a minute, gigabit 1 has no IPv6 config, so it's normal that we drop that traffic. So some drops are legitimate, some are not, but by using that CLI, you can find out which one is right. Do you think this feature would be useful?
It's late, you know.
Yeah. So, see. So to wrap up, you know, before you were troubleshooting from iOS down to the data plane. Now you can do the reverted way, which allow you to get information from the data plane, and that will open your eyes on what interface to check, what feature to check, and go the other way around, which allow you to be more efficient because you don't need to learn the configuration anymore. You just trace the packet and then understand where it goes into the config, especially if the config is very long. And this is very easy to do. Troubleshooting control plane of ASR, it requires TAC. But everything else, that's something that can be done by anyone. What question do you have?
So me and Olivier, we will be here for the next few hours, right? So you feel free to ask. I speak Polish, even Silesian, so you know we can talk in our native language. So just two more things. There is a bus going around, Cisco bus going around Poland between the 6th and 14th October in Gdańsk and in Warsaw. You can see some SP Wi-Fi stuff there. For the details, please refer to this webpage. And Gavo, I think you will be happy about this. So there is a Cisco Secure conference next week. Myself, I'm having there 3 hours on VPN troubleshooting. So please feel free to come, and there is the registration code which will give you 20% discount. And yeah, thank you very much.
Thank you for the lecture.